Alright, so we're going to demo KNEE3, right? We're going to walk through the entire registration, right? As we know, KNEE3 is imageless, right? So no CT data ahead of time, no MRI data, no x-rays required. We're going to build the three-dimensional model inside the computer, right? The way we do that is we fix a race of the bone and we build a model through a registration process. What we've done with KNEE3 is actually made the registration the fastest it's ever been and the most flexible, right? So as we work through this, I'll point out some of the features, right? We rotate the center of the hip and get a center or functional center of the hip, and that'll allow us to build a mechanical model of the bone. With our new clicker here, we can come down and take several points pretty quickly. As you can tell, I'm not looking at the screen because the fact checking in the software will allow it to determine if I was medial or lateral on these points and correct them. We've also built in a skip and skip always function here, which allows you to say, if I choose not to take this point, I can not take it today, or it can become part of my profile to not take this registration, right? But here I do want to take the condyle because that information is important to me. As I go through, I press once on the clicker and just work through these tic tacs here. If I want to take a longer registration, I can stay in each zone much longer and gather much more data. This will just be reflected back on the screen later. And I work all the way in posterior and then forward, just making sure to grab every one of these zones. Start up here on the ridge, follow the flange down, nice and quick. Ankle point, if I put them in reverse, the software would take it and flip around for me. Entry point into the tibia, rotation straight over. A single point on the tibial plateau to reduce the registration. And you're going to kind of want to pick the point in which you put a stylus later on, right? After that, you've built a full model of the bone on the screen, and you can put it through entire range of motion. And as you put it through range of motion, you're building a model of what's happened in the knee. So these models these plastic models are pretty awful at simulating real bone. But what we said is here we've got a graph that shows us that we're slightly more lax in extension over flexion. And the concept here is that we're taking gap balancing a step further and the soft tissue sleeve more serious. So as we look at it, we're going to say, you know, we can look at any part of the graph and know how our procedure is affected by taking different steps in the procedure. And for the first time, we're predictably modeling what's happening in a case. So if you look here, we have a graph that has medial and lateral collateral ligaments, 0 degrees flexion, 90 degrees flexion, 90 degrees flexion, 60, and for the first time ever, this anecdotal mid-flexion, right? Where we used to talk about or think about mid-flexion instability, for the first time ever, we can now see it, right? Visualize it on screen. Now, where this really comes into play is every step as I go through the procedure is going to be indicated on the screen, and we're going to know how each cut is going to affect the soft tissue envelope. So we know that by going to the tibia, we can universally affect both the flexion and extension gap. Now if you notice, I'll hold it right up to the screen, and as I just move this around slightly, you'll see that it automatically brings up the tibial information. So this is all gesture driven now. There's no more workflows, and the software follows me. So as the surgeon, I'm the one dictating what's happening in the case, right? And if you take a look at the graph, right, as I resect more bone or less bone, both the flexion and extension gaps tighten or loosen universally, because that's the impact of what happens when you take more tibia, right? As we take more or less tibia, the lines move away from center, right? Center is tight, away from center is loose, right? So we know that in the tibia, we can affect everything universally. In the femur, right, we know that a resection level, as we add it up, creates more laxity in extension. So here I am with a cut, and I want to go down to 0 degrees mechanical axis, right? And I want to put some flexion in here, so I'm just hand driving this now into flexion. But if I look at my resection level, as I take more, the bottom of the graph opens up, right? The extension, because extension is affected by the distal resection. And as I take less, the extension is affected. But the top of the graph at 90 degrees remains unaffected because the flexion gap is not affected by the distal cut, right? So as I move this up and down, only the areas that pertain to that portion of the procedure are affected in the graph. Now this gets to be really exciting when you take a look at a 401 block. So if I pretend that I'm going to my 401 cut, now I instantly, the computer follows me to my 401 cut. It gives me wide sides line, the posterior condylar axis, the transepicondylar axis. It gives me resection, posterior resections, and it gives me an anterior posterior slope of anterior posterior shift in real time. So now I can take a look at my graph and I can affect the discrepancy in the posterior condyles in real time. So if I wanted to loosen up the posterior gap, I can go for an anterior shift, right? And that'll affect an anterior shift, affects the top of the graph there. And as I rotate the component, we come to a balance, right? And if we think about this as a soft tissue, so we want to be in the neighborhood pretty close to what each one is doing, because it's not hard bone that we're affecting here, but it's going to be a soft tissue that'll have some accommodation of these cuts. And as I move here, the two lines move into parallel, and when they move to parallel, we know that means an even tension throughout the entire range of motion. And when we have an even tension through the range of motion, that means that we have a balanced knee through the entire range of motion, and it's a successful one. Here, if I find this is correct, with an anterior shift, that's a pretty considerable one, I can pin the block there. I can also downsize the component and achieve the same effect, and that'll affect the graph in real time.